So it's 5 minutes later, and you can see that the plate is now pretty frosty. I'm using this Arctic Silver heat transfer compound, which I've now discovered is really terrible at low temperature. I took this thing apart just a minute ago to see how it was doing, and the Arctic Silver on the hot side is fine. It's reasonably fluid at whatever the room temperature is in here at the moment, probably about 18-19 degrees. However, on the cold side, it's just turned to an absolutely thick putty. It's useless. So I'm going to have to find a low temperature thermal compound for the cold side. I'll probably still use the Arctic Silver for the hot side because its thermal conductivity is about 10 times higher than the kind of standard silicon-based thermal compounds. But yeah, a bit disappointed that it doesn't do the cold side as well. Hey ho. Now, I wanted to talk a bit about the maths of Peltier devices, because there's a lot of very hand-wavy information out there about how to design for Peltiers, and not a lot that's actually particularly constructive. Now, these things aren't super simple, but there are a few basic rules that if you understand them, then you can do efficient designs with Peltiers. So first of all, what is a Peltier device? I'm sure if you're watching this and you probably already have an inkling, it's a heat pump. It will push heat from one side to the other, heat energy should I say. So it has a cold side and it has a hot side, and what it'll do is make the cold side cold and the hot side hot. Now normally heat flows from hot areas to cold areas, but with the Peltier we can push heat uphill, as it were, and force heat energy to go from the cold side to the hot side and make the cold side colder than room temperature. Now, how does it do that? Well, it does it using something called the Peltier effect, or more generally the thermoelectric effect. Now, the two different people actually discovered this at the same time. There was a guy called Peltier and a guy called Seebeck, who within a year of each other made the same discovery, which was if you bond two dissimilar metals together and pass an electrical current between them, then you'll see a temperature difference, or vice versa. If you bond two dissimilar metals together and you have one junction hot and the other junction cold, what you'll see is a voltage across them. So that's the basis of thermocouples, temperature sensors, or Seebeck generators. All of these devices make use of this same principle, which is you bond two different metals together, you pass a current through it, you see a temperature difference, or you force a temperature difference and you see a current. So Peltier device optimized for pumping heat, which is what this is, or a Seebeck generator, which is optimized for turning a heat difference into energy. So you see these are energy harvesting devices. Ave did an interesting teardown of one that you stuck next to a campfire and it supposedly charged your phone. Well, the device in that looked like a Peltier but was actually a Seebeck generator. They're slightly different, but not very different. So this is a Peltier device. So now we know what it does and vaguely how it works. The real trick is getting it to work efficiently. So if you go online, what you'll find is a lot of people saying, oh, they're 10% efficient. So what does that mean? Well, they say, okay, so if you put 100 watts in electrical power, you'll get 10 watts of heat pumping, i.e. it'll suck heat energy from the cold side into the hot side at a rate of 10 watts for 100 watts in. That's what people will say is a good rule of thumb. They're not that bad. That is pretty bad, because actually what's going to happen here is the energy on the hot side, the energy that this heatsink is carrying away, is the sum of the heat energy that it's sucking out of this copper plate and the electrical energy that I'm putting in those wires. So at the moment it's got 12 volts across it at 15 amps. So it's got 180 watts of heat energy going into it, of electrical energy going into it. And at zero, so this particular Peltier, if we look at its datasheet, which we'll do in a minute, at 0 degrees temperature differential, so when the copper plate is at room temperature and so's the heatsink, it'll be pumping 150 watts of heat energy. So not bad. I mean, 150 watts of heat energy for 180 watts of electrical energy is certainly a lot better than 10% efficient. However, that means you've got 330 watts of heat energy being pumped into this aluminium block. So it's going to heat up fast. And in fact, at the flow rate of those pipes that I'm running this at the moment, it goes up by about 5 degrees above the temperature of the water on the inlet side. So the water on this side is 5 degrees hotter than the water on this side. So I've got that the right way? Yes, I have got that the right way around. So that's a lot of heat to deal with. So, and it gets worse. So the parameters of this Peltier device are the temperature difference across it, the amount of electrical energy we're putting into it in amps, as in the amount of amps we're putting into it, the voltage across it, and the power that we're putting into it, and the power that it will absorb on the cold side. And these parameters are all related together by graphs that you'll find in the datasheet. And what you've got to do as a designer working with one of these things is find your sweet spot, your operating condition for that Peltier where it achieves the result that you need to achieve. So for me, I want to cool a beer quickly. So I've got half a litre of beer in this thermally insulated container, so we can pretty much neglect effects of the beer absorbing energy from the air because it's in a thermos. It's, you know, these things are rated to keep warm for 8 hours. It's not over a 5-minute period, it's going to absorb a negligible amount of energy from the air. But half a litre of beer has a lot of thermal mass to it. Water is very good at storing energy, thermal energy. We'll go into the maths of how to calculate that, but off the cuff I can tell you that you have to extract 34 kilojoules of energy from half a litre of water to bring it from 20 degrees to 4 degrees. 34 kilojoules. So if we were doing this at a kilowatt, if we were pulling energy out at a rate of a kilowatt, that's 1000 joules per second. We would need 34 seconds to cool that beer, and that's monstrous. I mean, the best we can achieve here is 180 watts. So we know right off the hop that the best case scenario is going to be about 5 minutes. But unfortunately, with Peltiers, as I've already mentioned, as the temperature difference across them grows, the rate of heat transfer reduces and the voltage across them increases, which means the power they dissipate increases. If we drive this thing at 15 amps, at 0 temperature difference, it's only got about 9 volts across it. By the time we get to 70 degrees of temperature difference, which is the maximum this thing can do, it's at 18 volts. So it's dissipating twice as much electrical power and absorbing almost no heat energy at all. In those operating conditions, it's pulling maybe 5 watts of heat energy through it. It gets that bad. So what we've got to do to make this thing work efficiently is A, not let this copper get anything like as cold as it's currently got. You know, it's got a thick layer of ice on it now. I can just about rub through it with my fingernails. That is reducing the efficiency of the Peltier significantly. It's found an equilibrium now. It's not really getting any colder. It's probably pulling 10-15 watts of heat energy through it, which it's absorbing from the air at about the same rate. The ice insulates it and helps it get cooler, but it's still now at a very low performance equilibrium. So what we need is good thermal contact between this copper and the beer, because if this copper gets significantly colder than the beer, then our efficiency is going to suffer. So that's the first thing we need to do. The second thing we need to do is keep the hot side as cool as possible. We've got that pretty well stitched up. It's been running now for about 15 minutes, and this water, not even warm, just slightly warmer than ambient. The radiator is probably dissipating about a third of the heat that this thing is generating, and there's 5 litre reservoir there. Water has very high specific heat, so it takes a lot of energy and over a lot of time to appreciably raise its temperature. So we've got that going for us. That's an advantage. These things are so cheap. This aluminium block was about £4 on eBay, I think I got it from. The sump pump was about the same. The plastic pipe was probably about the same, and a bucket, a couple of quid. This is not an expensive cooling system. The real trick and the real thing that I've done here, which is how you engineer these things properly, is to really do the maths on a second-by-second simulation showing the temperature difference across the Peltier, and then using the data from the Peltier's datasheet to actually read off how much heat energy it's pumping, what effect that has on the beer, what effect that has on the cooling water and the hot side thermal block, and the rate of heat transfer between the copper and the beer. And we'll go into the maths, we'll go into the thermodynamics of how you actually model that second by second, and we can graph the results, and we can actually see on those simulations the beer temperature coming down, the heatsink temperature coming down, the cooling water temperature going up, and then we'll plot the efficiency as well. We'll be able to model the voltage across the Peltier, and therefore for a fixed current we can model power in the Peltier, and all of those parameters link together to give us the total efficiency of the system over a run period. And what we'll do is also vary the current in the Peltier over that time and see what effect that has on our efficiency. And I can tell you from the tests I've already done, at 15 amps the total efficiency is pretty bad, but if we run this at 9 amps the efficiency goes up significantly. It's just this particular Peltier is significantly better at lower current than it is at high current, and so we'll go through all of that.